In this screencast, I'm going to demonstrate how to use an interactive simulation that models an ordinary vapor compression cycle using the refrigerant R-134a. So the link is given here, and then a snapshot of the simulation where we show a pressure enthalpy diagram and indicate the direction of the process. We have a compressor, condenser, and then a throttle where we get cooling, and an evaporator to get back to saturated vapor. We can look at either pressure enthalpy diagram or a temperature entropy diagram, and we can control the two pressures, the condenser and evaporator pressure. And so let's look at the simulation. So here's the simulation. We can change the pressure, and as we lower the pressure, you'll notice the coefficient of performance is increasing. So the coefficient of performance is how much heat we removed in the evaporator divided by how much work we put in, since the objective is to remove heat. If we lower this pressure, we indeed increase the coefficient of performance, but we're lowering the temperature where we get condensation. So since we have to exhaust heat to a lower temperature, that means we have a smaller delta T, say, between the back of a refrigerator and the room air. And so we have much slower heat transfer, which would mean larger area for heat transfer. So we can raise the evaporator pressure. Coefficient of performance becomes very large, but now we've raised the temperature. Since as pressure goes up, the saturation temperature goes up, so we now have much less cooling, much less heat transfer, and we have much higher temperature that we can't cool any more than. So even though coefficient of performance is higher, it may not be a good way to operate if we're trying to cool something down. We can look at temperature entropy diagrams. As we said, as we raise this shows directly, we raise this evaporator pressure, we raise this temperature, we raise the condenser pressure, we raise this temperature. The actual cycle is here, and if we move the mouse over, it shows here we have saturated liquid. We go through a throttle, and we get two phases. This is where we get the cooling. And so the coefficient of performance, which is Q cold temperature, QC over work, is also related to the enthalpies that are shown here in the details. And so this is a common cycle for refrigeration, and so understanding its behavior on a pressure enthalpy diagram is valuable for understanding best how this process takes place and how changing variables affects it.